Alrighty, it's 12:30 with quick introduction. Firstly, welcome everyone. Thank you for joining today. We are happy to have you here and appreciate you taking the time to join this talk. Before we begin, let's take a moment to reflect on the land we are on and its history. We acknowledge that the land that we are meeting on today is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. We are most grateful and respectful for the use of this land. It is my pleasure to introduce our speaker for today's session, Professor Mario. Thank you for joining us today. He's an associate professor of actuarial science at the University of Waterloo and the Sun Life Fellow in International Actuarial Science. Prior to joining University of Waterloo, he held the positions of Director of Enterprise Risk Management at Canada Life and Assistant Professor of Financial Engineering and Risk Management at Imperial College London. His research focuses on dealing with risk and uncertainty in risk-sharing markets, insurance markets, etc. Today, he'll be sharing insights from his recent research on decentralized risk sharing, with a particular focus on peer-to-peer insurance, an emerging model that's gaining attention as an alternative to traditional insurance. We'll explore how this can be shared efficiently among individuals with different attitudes towards uncertainty. We're excited to learn from your work, Professor. Please take it away.
Thank you, Shaka, for the introduction, and thank you for the invitation. Hi, everybody. I see some familiar names here, so I just want to point out that I see you, Dongshan, Austin, Brandon, and Yushwan, and a few other people that I don't know. So again, thanks for the invitation. I hope you'll get something out of this presentation. My intention here was to have some sort of a general introduction to a field that's exciting to me, at least, which is the field of peer-to-peer risk sharing. I won't go in too much depth here, but I want to at least lay the foundations for the field for you. And hopefully there will be something that you'll find interesting. I see a lot of grad students here as well, so hopefully you'll take some ideas for future research here. Just let me mention before we get started, if you have questions, I don't mind taking them through the talk as I proceed, but I have to see you. I have to see you. So if I don't see the question, I won't be able to answer it. Maybe Vishaka, you can help me with that if that's okay. Okay,
Yeah.
so I would suggest you type your questions in the chat, and then maybe we'll try to get to it. Otherwise, I'm happy to answer your questions at the end.
Mhm.
Okay, so with that out of the way, um, a couple of things. I guess I want to start by defining briefly before we proceed. Just looking at the title here, let's try to analyze some of these words here. So foundations, as I said, I just want to give you a general introduction of the field with maybe one particular result that would be probably the most technical result that I'll present here, but otherwise it's mostly for you to understand what the field is like. So that's the first keyword, I guess, in this title. The second one is Pareto optimal. That's a classical notion of optimality in pure exchange economies, which is basically the foundation, the mathematical foundation, or at least the economic foundation for these models of risk sharing that we typically consider in the literature. We'll get to it in a second, but that's some criterion for optimality. That's basically the standard notion of optimality in this field. Lastly, peer-to-peer risk sharing or peer-to-peer insurance, if you like, is a special market model for sharing risks among individuals. And that you can look at that as a special case of a much broader literature on pure exchange economies in mathematical economics. And that is the foundation for these kind of insurance markets. So these are the three sort of keywords in this title I wanted to spend a couple of seconds on. And so just to take a step back a little bit, I guess one can look at risk sharing markets and classify them in two broad categories. The first one, which I like to call a centralized risk sharing market, that's your run-of-the-mill insurance market. So that's a typical model where you have an insurance company or a collection of insurance companies that act as the only suppliers of insurance in the market. Okay, and you have consumers on the other side. In other words, not everybody can mutually insure everybody else. So there's a clear separation between who can provide insurance and who is buying insurance. And again, this is the classical traditional model of insurance. And the basic construction here is the notion of an insurance contract, a premium payment that you as a consumer pay to the insurance company, in return for which the insurance company promises an indemnity payment when a loss happens. That's everybody's familiar with this model of insurance, so I won't spend too much time on this. In contrast to this, there is what I like to call a decentralized market for sharing risks, and that is basically based on the idea, a very old idea of insurance, as a matter of fact, of having a collection of agents mutually insure each other. Um, if you dig deep enough in the history of uh, financial markets or just insurance in general, this is the very first form of insurance. I guess it goes back to probably Mesopotamia or something like this. I mean, it's quite old. And this is how insurance really started, not in the sense that we give it today, in the sense of paying a premium and receiving an indemnity, but in the sense of mutually insuring each other as a community, basically. Okay. So when we talk about decentralized risk sharing markets here in this talk, just think about a pool of agents who want to mutually insure each other without having recourse to an insurance company a priori. Now, of course, they could resort to an insurer if they want to insure anything above a capacity, right? So suppose Austin, I'm not picking on you, but I just see your name here first. Suppose Austin, me, Dongshan, and a few other people, let's say 5 people, decide that we want to mutually insure each other against, I don't know, risks to our cars. Okay. The idea is we all of us put an amount of money in a pot, and then when one of us suffers a loss, we use this money in the pot to fix whatever happens to the car. Okay. Of course, you can extrapolate from this model, but that's the basic construction. Like I said, you can add an insurance layer to this, meaning suppose our pot is $100, but suppose there's a loss of $105. We can insure anything in excess of the pot through traditional insurance. Excuse me. So what I'm trying to say is that there's a hybrid between these two things, and these kind of decentralized products with insurance above a capacity do exist in practice. But here I'm only going to focus on the pure peer-to-peer decentralized risk-sharing market, meaning there's no insurance company on top of that. Okay. And the question here is, how will the agent determine a priori, meaning ex ante, before the loss happens, how would we determine the best or most optimal way to allocate this aggregate risk among each other? And by aggregate risk, I mean the sum of all the individual risks. And by optimal, I mean Pareto optimal, and we'll come to this in a bit. But that's the main idea here, okay? That's the main sort of economic umbrella behind these notions. One particular example that's useful for us in the insurance field is the notion of a peer-to-peer insurance arrangement or a peer-to-peer market. And this is a special case of risk-sharing market in many aspects. The first of which is that peer-to-peer insurance can allow for premium payments between individuals. Like I said, we put money in a pot, for instance. You can think of it as a premium payment that you pay to the pool. And then based on the amount of money you have in that pot, you can indemnify people, okay? Traditional risk-sharing markets are pure exchange markets of risks. There's no deterministic dollar amount payment from the get-go, okay? I'll come back to the technical aspect in a bit, but just think of it as it is a special case, the notion of a peer-to-peer insurance, with maybe a little bit of peculiarity due to the insurance nature of the market, okay? So I will not be able to summarize all the literature here for you, but I'm just going to give you a snippet and maybe a shameless plug of some of the work that I've done in this field before. But this notion of Pareto optimality in insurance has a long history, and it's a long history from mathematical economics, as a matter of fact. All of these foundations were economic theory foundations that were later on implemented within insurance setting. But everything goes back to the work of Arrow and Bork, essentially, and maybe also you can extend to the work of De Breu on general equilibrium. And all of these techniques were applied in an insurance setting. Now, there have been numerous extensions, and like I said, I'm not going to be able to cite all of this here. We can literally spend an hour talking about the literature. But I'll just mention a few of papers of mine in this direction that you might find interesting. Um, One particular aspect of this traditional field is that premium functionals or pricing mechanisms are typically determined ex ante before you issue an insurance contract. This is the classical approach. Recently there has been some interest in also endogenizing the pricing functionals themselves at an equilibrium, meaning determine what is an optimal pricing mechanism also at an optimum, rather than only determining what an optimal indemnity is. Okay, this relates to the work on equilibria and specifically the notion of a stackable equilibrium. There's a lot of work recently on this, and this has been probably my main research agenda in the past couple of years. So that's why also a shameless plug of some of my work in this direction as well. Now, having said this, this is not what we're interested in here in this talk. Here, we're interested in decentralized markets. Um, and like I said, the basic foundation here comes from welfare economics, the literature on efficiency in pure exchange economies and equilibria in pure exchange economies. Um, there also is a large history here, and I won't be able to do justice to this history by summarizing in a couple of seconds, so I decided not to mention any of these papers except the two foundational ones, the paper of Bork, the paper of Wilson, that has been done traditionally within the classical framework of decision-making, expected utility theory. Okay, and
Interrupt you, Professor. We can still see only your first slide, the title slide on the screen. Is that
yeah, that's surprising. So
that?
I'm glad you mentioned that now rather than half an hour from now. But let me try to share again here.
Okay.
Okay, you can see my slides now.
We're still on the PDF screen and we see the title slide.
How about now? Can you see anything else?
No, it's still the same.
Okay, bear with me for a second.
Yeah, no problem. Take your time.
I've literally done a million presentations. This is the first one, the first time this happens.
That's okay.
Can you see the slides now?
Yes.
What page can you see?
On a slide that's titled Risk Sharing Markets.
Okay, good. Okay. Yeah, so just make sure that can you see the slides moving around?
Yes, yeah.
Perfect. Okay. So
Thank you.
this is everything I was mentioning earlier here. And we stopped around here. So I was saying that the main concern of the classical literature on risk exchange is determining Pareto optimal allocations, which I will define in a second. But the classical characterization due to Bork says the following. Something is optimal in the Pareto sense, and granted, I will define this in a second, if and only if this is a state of the economy where the marginal rate of substitutions between different states of the world for agents are equal, meaning nobody has an incentive to deviate at the margin because they won't gain any utility at the margin. This is a classical and very foundational result in the field, which I will come back to later on in a more mathematical way. But essentially, this is the economic interpretation of it. Now, one immediate implication of this is the fact that Pareto optima or optimal allocations in risk exchange markets will be monotone functions of their sum, and therefore they will be comonotone, meaning they all move in the same direction. Okay, we'll define this again formally in a second. Are you still able to see the slides moving? Perfect.
Yeah.
Okay, so this has also been extended in the literature beyond the classical expected utility model to account for more general preferences, maybe to account for ambiguity in preferences, to account for lack of information and how you represent that, etc. And all of these results hold under risk aversion, but risk aversion needs to be defined in a slightly more general sense than within the classical expected utility theory. It's rare to get explicit closed form results for Pareto optima, but in some generally general enough cases, I guess, you can obtain them. And I've been working on this in the past couple of years. I'll focus today on this first paper here. The other ones, maybe I'll mention in brief what's happening, at least in the first part of this talk. So there will be two parts to this talk. The first one is about risk sharing between risk-averse agents who maybe have robust utilities, so they are sensitive to ambiguity. And the second part will be asking the questions, what happens when you introduce in a collection of risk-averse agents a few risk-seeking agents? You can imagine that this will disrupt sort of the nature of the equilibrium, and indeed that it would, but the question is in what sense would it, and is it predictable? And I will give you answers to all of these questions throughout this talk. So, excuse me, in the first part, we're going to talk about peer-to-peer insurance for a general enough class of utility functionals that can be seen as representing ambiguity or uncertainty about the state space. And I'll make this a little bit more clear as we go along. And I'll show you how we were able to characterize Pareto optima in a pretty nice way and a pretty implementable way algorithmically, which I found to be quite interesting when we were working on this, especially the fact that the theorem, as I'll show you later on, is essentially an algorithm. It gives you an algorithm to implement Pareto optimal allocation. So I can, if you give me the preferences of the people and their initial risks, I'll be able, through a theoretical result that you can implement numerically, to tell you exactly what Pareto optimal allocations look like.
No.
Okay? Guys, please mute yourself unless you're Vishaka. Thank you. And in the second part, and the second part, we're going to, like I said, focus on introducing risk-seeking agents in a peer-to-peer insurance pool and see what kind of results you'll get from that. Intuition would basically say the following. If you have a risk-seeking agent or agents, they will have sort of an incentive to introduce randomization or randomness in the economy beyond what the initial risks of the agents are. And that indeed is what you would observe. And I'll show you a few of these results. Essentially, what I want to show you in that part is that there is an optimal way to share risk among these mixed populations, mixed in the sense of risk attitudes, some risk averse, some risk seeking. And it turns out that all the risk averse people will share risk comonotonically within themselves, and all the risk seeking people will share risk counter-monotonically within themselves. I'll define all of these later on. Okay, so again, the first part is based on these two papers. This one is with my previous PhD student, Michael, who's now in Hong Kong. And this one is also with Michael and with a colleague of mine, Alfred, who just recently moved to Hong Kong as well. The second part is based on three papers with my colleague Rodu and our PhD student Xinghua. Xinghua is on the job market if anybody's interested. And we'll get to some of these results in a second. I won't be able to cover all of the results of these three papers, but I'll mention some foundational points before we get there. Okay, before I get started, any questions so far? Okay, good. So let's move on then with basically underlying the model and introducing these notions of allocations, preferences, and Pareto optimality. The basic market structure is like this. We're going to start with an L infinity space that we're going to consider to be the space of all acceptable risky positions, or more generally endowments. So just to clarify, throughout this talk, when I mention endowment, that's something that could take positive or negative values. It's basically levels of wealth, okay? You can lose or you can gain, and hence the positive or negative. When I mention risks, I strictly mean elements of L infinity plus. Risks are positive random variables, and a positive realization is a loss, okay? So endowments can be signed, whereas risks are always positive, just so that we're clear on the terminology. So this setting is a bit more general than a setting of sharing risks, because you're allowing these positions to also take negative or positive values. So think of them as wealth levels. You have n agents in this economy. Each one is initially endowed with a endowment xi. And let S be the sum of these xi's, and S is something that we're going to call the aggregate endowment in the economy, the total amount of wealth in the economy as we start, okay? The question is, how, or is it or can we improve on the initial allocation of these endowments so that everybody is better off? That's the basic question. How can we redistribute the S among everybody such that everybody prefers whatever you offer them rather than their initial starting point xi? Okay, but we have to do this in a way to preserve the aggregate wealth in the economy. Hence, this introduction of the set A, which is the set of feasible allocations of the aggregate endowment. So A stands for allocations. And an allocation is any n-dimensional vector of random variables that sum up to the aggregate wealth. Okay, so it's just a way to redistribute the wealth among the pool. And hopefully, we want to find some vector yi star, I going from 1 to n, that makes everybody better off. Okay, at least better off than xi, but it makes everybody better off in the sense also of optimality, right? Meaning that nobody can improve on this allocation. And if somebody improves, somebody else has to suffer. Okay, so we want to find an allocation upon which nobody can improve. That's basically the goal. And we'll define this mathematically in a second. Now, we're going to assume that every one of these agents has a preference relation on these endowment positions that represented by some utility functional ui. Okay. And just as a side note, I'm approaching everything here from the perspective of utilities rather than risk measures. So utilities of wealth rather than measures of risk exposure. But there's a duality here that you can map this setting completely to a setting of risk measures by defining for a given utility functional ui, you can define a risk measure rho I in this way, right? So rho I of z is minus ui of minus z. And you can translate everything now in the language of risk measures. So rather than maximizing utility or minimizing a risk measure, all of the results would hold. Nothing would change, okay? A few definitions before we proceed to the results. So we're going to say that an allocation is individually rational if it incentivizes everybody to participate in the market, meaning it gives you an improvement over the status quo. The status quo is your initial endowment, okay? So something is individually rational if it makes everybody better off. But that doesn't mean it's optimal. You can have many ways of improving, but maybe a few of them are optimal. We're going to say that something is optimal or Pareto optimal if first it is individually rational, and you cannot find any other individually rational allocation that gives you an improvement over the y star for every agent, and at least one strict improvement for one of the agents. Okay, that's just a definition. So something is Pareto optimal if you cannot improve on it for everybody and have a strict improvement for at least one person. If that's the case, meaning if you cannot find such an allocation, then yi star will be called Pareto optimal. And our goal here is to find Pareto optimal allocations because, as you can tell from the definition, this is something upon which you cannot improve in the economy, basically. Okay? Questions about this? Okay, so let's denote by PO the set of Pareto optima and by IR the set of individually rational allocations. And like I said, our main goal is to find Pareto optima, but that is going to depend on the properties of the utilities that we have here. So let's define a few things before we proceed. As a side note, you can also specialize this definition to comonotone allocations, and that will be handy in a second. So let's introduce this definition. First, remember that two random variables are said to be comonotone if they always move in the same direction. So mathematically, a vector is comonotone if for any I and j, meaning for any two selections from this vector, these two random variables always move in the same direction. If one increases, the other one has to increase. If one decreases, the other one has to decrease. So the product is always positive, okay? If the product is always negative, we say that the vector is counter-monotone. And let AC be the set of feasible allocations that are comonotone. Okay? So we can specialize the notion of optimality now to only those comonotone allocations. Basically, think of the general market that we examined earlier and think of a sub-market, an incomplete market, which is only comonotone. Okay? So you can't just redistribute in any feasible way. It has to be feasible, meaning preserving the aggregate endowment, but also comonotone. Okay, so that's a major restriction in terms of market structure. But later on, I'll show you that, as a matter of fact, all Pareto optima will be comonotone. So there's no loss of a generality on the risk aversion. There's no loss of generality by specializing the larger market to the smaller comonotone market. Okay, One of the results later on will be to show that comonotone Pareto optima are exactly equal to Pareto optima. The two sets are the same. And that's actually a major result from the classical literature that we were able to extend to more general settings here. Okay, good. So before we proceed, let's talk a little bit about utility functionals, their properties, and I'll show you some of the results. So a few definitions that you might be familiar with. Monotonicity of a utility functional means pointwise monotonicity on L infinity. Translation invariance means if you put a constant inside of the utility is the same as putting it outside of the utility. Concavity of the utility function is in the sense of concavity of functionals in general. Positive homogeneity means that if you multiply z by a lambda and you apply your utility functional, it's the same as multiplying by lambda the utility evaluation of z itself. Low invariance means that if two random variables have the same distributions, then they have the same level of utility. And finally, combinatonic additivity of a utility functional means that the functional is additive only over combinatone random variables. Okay? I'm sure everybody's familiar with this, so I'm not going to spend too much time on this. One extra definition that might be new to you, but think of it as the dual notion of a convex risk measure. A utility functional is said to be a monetary utility if it's monotone, translation invariant, and concave. And like I said, this is the dual notion of a convex risk measure. These low invariant monetary utilities have played a very important role in risk sharing. There's a large literature on this, and I'm not going to spend too much time on it. But for the PhD students out there, if you're interested in this topic, I suggest two books. The one on the left is a wonderful reference by Ludger Ruschendorf on many topics related to risk sharing and beyond. I highly suggest you take a look at this. You can download it. You can download the PDF through your library website for free with a university affiliation. The one on the right is the newest edition of a fantastic book by one of my colleagues, Alex Sheed, and his co-author, Hans Vilmer. This is a wonderful resource. I suggest this to every one of my PhD students. And if you don't have this book, it's time to go out and get it. And I don't get any cut from this, by the way. It's just I'm a big fan. That's all. So these are great references for all of the topics that we'll encounter here and maybe some more general theory or some related theory. So I highly suggest you take a look at that. Okay, so in general, it's hard to get a closed form expression for Pareto optima. Typically, what the literature does is describe Pareto optima. Are they comonotone? What kind of qualitative properties of these can we obtain? But it's hard to get a closed form expression of these objects. What do they actually look like, right? To do that, typically the literature had to assume some stringent requirements, like for instance, quantile-based risk sharing. You can see that in a series of papers of my colleague Rodu and his co-authors. What I'm going to show you here, based on this recent paper with Michael, is that we are going to be able to get a nice expression and a nice algorithm to implement this that expression for Pareto optima when you have preferences that are low invariant, positively homogeneous monetary utilities. So monotone, concave, translation invariant, positively homogeneous, and low invariant. In essence, this is a low invariant coherent risk measure. First of all, we know that they would look like this, and I'll remind you later on of this result. They would look like worst case distortion risk measures, if you want, or worst case URI dual utilities over sets of distortion functions. And I'll show you later on how we can get a clear sort of characterization of Pareto optima in the setting. Okay? To do that, it's always a good idea to try to find an operational characterization of Pareto optima. If you want to go back to the definition of a Pareto optimum and check whether or not some allocation is Pareto optimal, it's a task that will never end, because essentially you're going to have to take an allocation and compare it to potentially infinitely many allocations to see if you can get an improvement. Okay? If you get no improvement, then it's Pareto optimal. This is not operational. And typically the literature tries to find equivalent ways of characterizing Pareto optima. I'm going to give you here a general characterization. It's known in the classical literature as the Negishi approach. after the economist, Japanese economist Negishi, who introduced something similar in an expected utility framework a long, long time ago. This is a much more general result here. It only relies on monotonicity and concavity of your utility function. That tells you the following. Something is Pareto optimal if and only if you can obtain it as a solution to a weighted sum, to maximizing a weighted sum of the individual's preferences for any given weight vector, lambda. Lambda itself is not basically the important factor. Lambda is just a parameter to parameterize your set of Pareto optima. This is a general result, and you see this is a much more operational result. In a sense, fix a vector lambda, solve this optimization problem, the solutions will be Pareto optimal. This is much easier than finding Pareto optima through the definition itself. There's an even easier result when instead of concavity, you have translation invariance. In this setting, you can show that something is Pareto optimal if and only if it maximizes the sum of the utilities. That problem itself, the soup of the sum, this is called the soup convolution. And in the context of risk measure, this is equivalent to the inf convolution, the inf of the sum of the risk measures. Okay? So this is going to be the starting point for us to characterize the solutions. Shaka, how much time do I have left here?
You have about like another 15, 20 minutes.
Sounds good. Okay. So let's talk a little bit about comonotonicity of Pareto optima and the risk aversion, and then you'll see why this notion of comonotone Pareto optima is indeed useful. Remember, this is a much smaller market than the general market, but like I said earlier, and we'll formalize this here, when you assume risk aversion, there's no loss of generality by restricting to the smaller market because you know that Pareto optima will actually be in the smaller market. Okay, that's the main idea or the main result here. But to be able to define risk aversion in a general setting, we're going to have to take a little bit of a detour. In the general setting, risk aversion, remember, general setting, you don't have a small utility functional u and then an expectation of the u. You have just a general mapping from a set of random variables to R. So how are we going to define risk aversion in the general sense? The definition here is based on the concave order. We're going to say that something is sure concave if it's monotone with respect to the concave order. So remember what the concave order is. The concave order says the following. Z1 is smaller than Z2 in the concave order if and only if for any concave utility or for any concave function u that's not necessarily monotone, just any concave function u, the expectation of u of Z1 is less than or equal to the expectation of u of Z2. That's the concave stochastic order by analogy to the convex stochastic order, okay? So we say that something is sure concave if it preserves the concave stochastic order. This turns out to be how you define risk aversion based on this result of a brilliant person in the field, Rosanne Dana, who's now retired, but she has contributed significantly to this field. One of these results in one of her papers said the following. A mapping, U or any functional in general, that is assumed to be concave and upper semi-continuous. You can forget this upper semi-continuity for now. Just think of it as a mathematical requirement that's needed for some proofs, because some of the proofs are by approximation, and you need to be able to preserve stuff through approximating, hence the upper semi-continuity. But let's say concavity, okay? Under concavity, sure concavity is equivalent to low invariance. This is actually not too hard to see, not too hard to prove. But most importantly, under concavity and monotonicity, low invariant is equivalent to being second order stochastic dominance preserving. And this is how traditionally strong risk aversion is defined in economic theory. So if you open an economic theory book, they define strong risk aversion as monotonicity with respect to second order stochastic dominance, and that's related to the convex order. I'm not going to go over these definitions in too much detail. I just wanted to mention to you here the connection between show concavity and risk aversion. So for us here, risk aversion is basically preserving the concave order, okay? So let's see what we can do with Shore concavity. It turns out that under Shore concavity, we have a very nice structure for Pareto optima. Pareto optima will be comonotone. And so, like I said, you can restrict to the smaller market. And that's this proposition. Forget the UPF and CUPF for now. I'm going to skip this. I just want to mention a couple of things here. First of all, if we assume that everybody has a monotone concave and risk-averse function, UI, so short concave, then the following hold. You have comonotone Pareto optima if and only if you have Pareto optima, meaning if one of these sets is non-empty, then they are both non-empty. More importantly, if you take Pareto optima and select from them only the comonotone allocations, this fully characterizes the set of comonotone Pareto optima. This is an important equality here. And even more importantly, if everybody is strictly Schur concave, meaning they preserve the strict concave order, okay? If you preserve the strict concave order, then PO and CPO have to coincide, okay? Meaning this becomes stronger. It becomes actually this, okay? So PO is actually inside of AC. This is what this is saying. So if everybody is strictly risk averse, then Pareto optima will be exactly comonotone Pareto optima. The two sets are the same. And therefore, you can restrict your market to the smaller incomplete market, the smaller market that's comonotone, without losing any information or without any loss of generality. And so this is going to be our guiding sort of thought here in the rest of this section, meaning we're only going to focus on finding comonotone Pareto optima because under strict risk aversion, these are the Pareto optima themselves. Okay, let me skip this here for a second. And let's assume that we have utilities that are concave. If they are monotone, risk averse, translation invariance, and positively homogeneous, then they have this following representation. And these will be the utilities that we are going to consider later on. So think of them as worst case or robust Yari dual utilities. I'm assuming we're all familiar with this object. This is a Choquet integral. If you're not, raise your hand and I'll explain it briefly. I see something in the chat here. Yes, send a question immediately. I'm going to stop for 5 seconds. Send a question here. If you don't know what a Choquet integral is, I'm pausing 5 seconds. Ask a question, I'll explain it. Otherwise, I'll move on. 5, 4, 3, 2, 1. Okay, so we all know what a Choquet integral is. So our utilities here are worst case Choquet integrals. Worst case with respect to the distortion function itself. And more importantly, we know where these distortion function lie. Like we know exactly what the set of distortion function looks like. They are basically integrals of quantiles, okay? So hence they are convex because their derivative is monotone increasing, okay? This is a nice result. It's not a result due to us. It's actually in the literature on risk measures. This is basically the Kusuoka characterization of low invariant coherent risk measures. But in the language of utilities, Dana gave this refinement of Kusuoka through the characterization of the set itself. And that turns out to be very, very important for us in the result that I will show you in a bit, okay? So this brings me, I guess, to the result that I wanted to talk about, which is the following. Let's define S underbar to be the essential inf of the aggregate endowment. By the way, when you talk when you talk about risk sharing, meaning the special case here where all of the individual xi's are positive, this S sub bar will be 0. The essential inf will be 0 because everything is positive random variables, okay? But more generally, it doesn't have to be 0. It's let's denote it by S sub bar. Let G be the set of all functions that are non-decreasing and sum up to the identity. Our main result here, which is going to give us an algorithmic implementation of Pareto optima, is the following. Let's suppose that we're in a market where all the agents have monotone concave, Schur concave, positively homogeneous, and translation invariant utilities, meaning, first of all, they are monetary utilities that are risk averse and positively homogeneous. Okay, then we know that they look like this based on the previous representation of Dana. And more importantly, we know what the Pareto optima are going to look like. So first of all, CPO is non-empty, PO is non-empty. So we do have Pareto optima in this economy. They do exist. And we do have comonotone Pareto optima. And like I said earlier, if on top you assume strict true concavity, then PO and CPO would coincide exactly. Otherwise, PO intersected with AC is equal to CPO, okay? More importantly here, we're going to have this very nice crisp characterization of Pareto optima based on this algorithm. Now, this is a bit of a mouthful, so bear with me and I will walk you through this. First, let's look at this result independently. Um, Suppose you have this problem of minimizing through the choice of the distortion functions of the individuals. So you're picking a distortion function for every individual, so Ti for every I, such that you are going to minimize this integral. Okay, that integral is the integral of the maximum over all agents of the tail evaluation. Okay, so this here, S larger than this event, is a tail event for your aggregate endowment. This P of this event is the baseline probability that people aren't aware of it because people distort these probabilities, but that's the baseline objective survival function of the endowment at this level. Every agent is distorting this through their subjective perception. So this is the subjective assessment of agent I of the likelihood of this tail event. Okay? Now, take the most optimistic assessment. Keep in mind, these are wealth levels. So that's a good thing, not a bad thing. In the language of risk measures, this will be a bad thing because you don't want your risk to exceed a certain threshold. Here, you actually do want your endowment to exceed a certain threshold. So this is the most optimistic agent in terms of likelihoods of the tail event. You're aggregating over the tail events, and then you're taking the worst case of all the distortion functions of this evaluation. You can see there's levels to this, and I'll come back to this when we describe the algorithm. But the point is that there is a solution to this problem, and this solution will be useful later on in characterizing the optima. And this is how we're going to characterize the optima. So an allocation is Pareto optimal and therefore Combinaton Pareto optimal under risk aversion. Keep that in mind. If and only if it looks like this. It's some function gi of the aggregate endowment minus the essential inf that you add to some deterministic payment ci. These are transfers. Okay, so these are called equilibria with transfers in economic theory. So you have a deterministic transfer of money between people so that the sum of these transfers is equal to the essential inf of the aggregate endowment. Again, if you have risks, this will be zero and this will be zero. Okay. More importantly, the GIs are constructed explicitly like this. Pick any set of distortion functions that solves this problem. That's denoted by T1 star to Tn star. For every X associated with the tail event, this tail event for the aggregate endowment, let Lx be the set of agents such that under this this collection of distortion functions, these agents are the most optimistic about the tail event. That's what this is saying, okay? So Lx for a given X is the set of agent who under this set of distortion functions have the most optimistic subjective assessment of the tail event. Guys, sorry if you hear construction noise. We have construction going on campus here at the University of Waterloo. I hope this is not too annoying. So once you do that, once you fix the Lx, choose functions h1 to hn that map r plus to 0, 1 such that the following hold. They have to sum up to 1 over for this x over the set of agents that are the most optimistic. And for the other agents, they have to sum up to 0 almost surely. And construct the g as the integral of this h. Okay, I know it's a mouthful, but at least you can see that it's a clearly implementable algorithm. Once you construct the G like this is going to give you all of your Combinaton Pareto optima. And you can think of the G as the marginal allocation of risk, because that's basically you're characterizing the G. Sorry, you can think of the H as the marginal allocation of risk, because you're characterizing the risk allocation through its derivative, HI. HI, you can think of it as a marginal risk allocation. Okay, so just to paraphrase this result in terms of how you can code it actually numerically as an algorithm, it goes like this. Define this function psi that takes two inputs. The first is a collection of distortion functions. The second one is an x corresponding to a tail event and gives you as an output the most optimistic assessment of the subjective likelihood of this tail event over agents for this given set of distortion functions. Step number one. Step number two, aggregate this through the functional psi tilde, meaning integrate this over x. Integrate psi over x to basically get this object here. this is going to give you this object here, essentially, okay? So that psi tilde is going to be an aggregation of this function over tail events to get rid of the second dimension of the psi, essentially, by just integrating it out, okay? Once you do that, choose a collection of distortion functions that minimize this. Remember, we have shown previously that the problem of minimizing this actually admits a solution, right? That was one of the results in the theorem. So pick any minimizer to this aggregation of the function psi. For that minimizer ti star, and for any given x, define Lx to be the set of individuals who are the most optimistic about the likelihood assessment of the tail event under this worst case distortion profile, okay? Once you do that, you can construct your functions h like before, and you can integrate the h to get the g's. This will give you a full characterization of your common-tone Pareto optima. And you can see this is implementable. You can implement this numerically. As a matter of fact, I have a student working on this. But yeah, I mean, I haven't pushed this in this numerical direction that much yet, but I think there's a lot to be done here. I'll come back to this point at the end because I want to talk about some further directions. You can get many special cases of this, and in the interest of time, I'm going to skip all of that. You can also introduce belief heterogeneity here, meaning you can have different baseline measures for every agent, and you can get a similar result. We do that in the paper, but again, I'm not going to talk about it because there's not enough time. I want to move on to the second part here and show you what you can do when you introduce risk-seeking behavior in the market. So let's now shift a little bit just for fun and talk about risk measures rather than utilities. Again, you can do everything in utilities or risk measures. It doesn't matter. But just for a bit of variety, let's assume that everybody has a distortion risk measure here, and that's how you measure preferences. And our goal is to find Pareto optima for these distortion risk measures when people are of mixed risk attitudes, meaning some of them are risk averse, some of them are risk seeking. And in the language of distortion risk measures or Yari dual utilities, risk aversion is equivalent to concavity of the H, and risk seeking is equivalent to convexity of the H of your distortion function. Okay, so this is how we're going to separate individuals into two types: those that are risk averse with a concave distortion, and those that are risk seeking with a convex distortion. And we have an economy with these two kinds of people, basically. And the question is, can we characterize Pareto optima when you have this mixture of risk attitudes in the market? Remember from before that when your utilities or risk measures are translation invariant, which is the case for distortion risk measures, then Pareto optima, finding Pareto optima, is equivalent to minimizing the sum of the individual positions. This minimizing the sum, this has a special name I alluded to earlier. This is called the inf convolution. And because of translation invariance, we know that something is Pareto optimal if and only if it attains the inf convolution, essentially. Okay? So to find Pareto optima going forward, we're going to focus on finding the inf convolution of these risk measures. Again, when we have people that are mixed, risk averse and risk seeking in the same market. So let's see what we can do with that. Let's assume that the first M agents are risk averse with a concave distortion function, each one distortion HI, and the remaining N minus M people are risk seeking with convex distortion functions HJ. Okay, they're all different. Let's define G1 to be the minimum of all of these concave functions HI. And by the way, a minimum of concave functions is concave, so G1 is indeed concave. And let's define G2 to be the inf convolution of these convex functions. And by the way, inf convolution of functions, not risk measures, is defined similarly to risk measures. That would be the definition here of G2, okay? So G2 will be convex by construction, and G1 is concave by construction. What we're trying to do here is to show that G1 can be seen as a representative agent for all the risk-averse agents, and G2 as a representative agent for all the risk-seeking agents. And indeed, you get that in the following result. So this theorem, which is the first basic result of the series of papers, and that's the only one I want to show you today, says the following. Something is Pareto optimal in this market with risk-averse and risk-seeking people if and only if The following holds. As a matter of fact, this is not just an implication. There's an implication in the other direction under some strengthening of the assumptions. That's why I said if and only if. But here I just want to focus on one implication, characterization of Pareto optima. So take something that's Pareto optimal, then we know that the following has to hold. This equality holds by definition of Pareto optima, essentially, which is basically, if you want, by this proposition. By this proposition, because of translation invariance, we know that the inf convolution is attained at this collection. So that's nothing new. The new thing, however, is that, and I think this is the beauty of this result, is that it shows that in this market, Pareto optima are attained as an inf convolution between these two representative agents. Okay, so remember, this is the agent representing all the risk-seeking people, sorry, risk-averse people, and this is the person representing all the risk-seeking people, right? So essentially, what you obtain in this market is that Pareto optima can be obtained as optima in a market with only two people, one risk averse and one risk seeking. I think this is a great result, and that was indeed an important first step in the rest of the work that we did with Rodu and Xinghua on this. The second part of the result says the following. If not only do you have concavity and convexity, but you have strict concavity and strict concavity of your and convexity of your distortions, then you can show that the optimal allocation, the Pareto optimal allocation y1 to yn, is basically two vectors that you're connecting to each other. The first one is all commonotone, and these are all the risk-averse people. And the second one is the remaining people who are risk-taking, is counter-monotone. Okay, that also is a nice result. I like the symmetry in this result. And that turns out to be quite a nice result for all future results that we developed in this paper. There's much more to do, and we do quite a lot more in this paper, or this series of papers, if you want, these three papers here. But I won't mention more than this. If you want, feel free to send me an email. I can send you a copy of these, or you can find them on my website. Okay, so I want to conclude with a couple of open questions for the PhD students here in the audience that might be interested in this. So remember, we had two parts in this talk, right? The second part was what I just mentioned about what we do, what can you do when you have risk-averse and risk-seeking people wanting to exchange risks, knowing that risk-seeking people have an incentive to introduce more uncertainty, and risk-averse people don't like this extra uncertainty. So there's this tension that you want to resolve. And in the first part was basically the market where you have risk-averse people, and you want to look for Pareto optima under various assumptions on the utilities, including ambiguity, etc. We assumed in the first part that our utilities are translation invariant and positively homogeneous, among other assumptions. But these were two key assumptions that gave us the representation as a worst-case dual utility. Now, from the perspective of risk measures, right, these are normal and natural assumptions to impose. As a matter of fact, they are quite standard. Translation invariance or cash additivity means that adding cash injection doesn't essentially increase the riskiness because money is not risky, essentially, okay? Right now, maybe it's a bit of a stretch. Gold is probably not risky, but let's say that money is not risky, okay? And positive homogeneity basically means that scaling by changing currency, for example, doesn't essentially change your risk exposure, okay? So the risk of a position is proportional to its size. That's what positive homogeneity means. These are very natural for risk measures, but for utility functionals, these are very weird assumptions. It's very strange to assume that a utility is indeed translation invariant or even positively homogeneous, because essentially people have diminishing marginal utility of wealth in expected utility theory, right? So the concavity of the utility means that the more you have at the margin, the less you're going to be satisfied with the addition, right? More generally than expected utility theory, you can still have this sort of phenomenon, but exhibiting this phenomenon will come at basically the expense of translation invariance. So there's always this tension between translation invariance and diminishing marginal utility, okay? So like I said, from the perspective of decision making, this is a strange assumption. So can we dispense of these? Can we get rid of translation invariance and or positive homogeneity and see what we can do in terms of characterizing Pareto optima? Let me briefly mention one idea here. If you drop positive homogeneity, you have the following representation Essentially, this is similar to how you represent convex risk measures, right? But in the language of utilities. You have this following representation of your utilities that are low invariant and monetary, but not positively homogeneous. Okay, so you have this penalty term, essentially, the added penalty, excuse me, the added penalty term. And that comes from basic convex analysis. This is just differential conjugate. What can you say about Pareto optima when you have these kind of preferences? A partial answer is that we know that they exist and we know that they are common based on these two milestone papers in the literature, especially this one, Ravanelli and Svindland. But can we go a step further beyond simply characterizing the existence? Can we say something about what they actually look like? The short answer is there's nothing out there, and I guess I've made some partial progress in two separate projects in this direction. But if anybody's interested in this, please feel free to reach out. I'd love to talk about this a little bit more. This is a very interesting problem, and it's not an easy problem to address by any means. I mean, quite complex, and I'm happy to talk about it more if you like. One other question, just sort of a general question that I'm just leaving out there for anybody who's interested. How much of the reinforcement learning or neural network literature can be applied to finding Pareto optima? Okay, I don't care if it's a black box. I just want to see how this black box works in the setting of Pareto optima. If anybody has an idea or wants to talk about this, feel free to reach out. I'd be more than happy to. So the last question I want to leave you with is the following. In the second part, we restricted the preferences of the individuals to RIARI utilities or distortion risk measures if you want. Okay, so you have just a Choquet integral representing your preferences. And therefore, of course, this comes with all the nice properties of Choquet integrals, common-tone additivity, translation invariance, low invariance, all of these nice things. Okay, in particular, translation invariance or cache additivity. So the question is, can you drop translation invariance and obtain sort of similar results? But this has to come with a slightly different definition of risk aversion rather than just concavity and convexity of the distortions. You will need something else here. And I suspect that this has to do with short concavity and short convexity. Okay. So can you still have a representative agent construction beyond Yari dual utilities? Again, if you want to talk about this, I'm more than happy to. Feel free to reach out. And I will stop here. Thank you. I'm going to skip this real world application. Thank you for being so patient and sorry for running above time.
No problem. Thank you so much. Do we have any questions? Feel free to unmute yourselves or put it in the chat.
Dongshan, I want to hear a question.
Well, yeah, thank you, Mario, for the wonderful talk. Yeah. So the thing is, I'll have to leave for the meeting soon. I was about to ask you about some real-world applications. Let's skip. Maybe you can talk about that to some PhD students. Yeah, maybe
Well,
it will.
wait a second. Since you're here and you want to hear about real-world applications, I'll briefly mention one quick thing. I think peer-to-peer is really useful when there's no proper insurance market penetration, right? Like, for example, agricultural insurance has been a pain for every government around the world, and I've really studied this deeply in the past couple of years. I looked at all the examples that have been implemented in Australia, in Canada, in the US, some places in Europe, and it always comes down at the end to government subsidy, which is not what you want an insurance market to be. It's not the government subsidizing you. That's not insurance. Okay. So one potential application, in my view, is to impose some sort of a peer-to-peer structure, localized geographically, or maybe diversified even better across geographies, right? Between farmers, directly between farmers, right? So we have a partial result in a paper with my colleague Alfred Chong and my colleague Tim Boonen, where we show how peer-to-peer with geographical diversification across states. For instance, let's say you have a bunch of farmers in Iowa and a bunch of farmers in Texas and a bunch of farmers in, I don't know, New York, okay? Because of the geographical diversification, you can actually obtain a strict welfare improvement over classical insurance market models. So I would like to examine this a little bit further, but this is the extent of the work we've done in this direction. Okay, hopefully that answers your question.
I see a question in the chat here. I can read it out for you. Would the neural network approach arise in the representation of the marginal risk allocation? It's by Austin.
Yeah, Austin, thank you for the question. So what do you mean arise? Like, I mean, I guess when you have the HI the way we characterize them, there's no need anymore for neural networks. What I had in mind was basically just give the algorithm, give the black box the risk measures themselves, and let the black box learn how to eventually get to a Pareto optimum based only on the risk measures and on the initial risks, right? If you give them already the HIs, you've already gave them the Pareto optima. So there's not much more work to do. I don't know if that answers your question, Austin. Yes, no? Oh, for the neural network to learn the HI as an output, yes, there is. Yeah, sure. I mean, keep in mind in this algorithm, the main complication was the fact that the T star is not constructed but obtained as a solution to some abstract problem, right? This is your T star here, the collection of T's, right? So you have to first solve this problem star here and at the bottom of the page. And that problem star will have a solution, will have potentially infinitely many solutions. This algorithm depends on one particular choice of the solution to that problem star. So one particular choice of the vector T1 to Tn star. It doesn't actually construct this. It takes it for granted as given. So one thing that the neural network could do is learn to find these T stars. And once it does, the rest follows through by just implementing this algorithm. Yeah. Maybe it's easier if you unmute yourself, Austin, rather than typing.
Yes, sir. I'm headed up to the airport. Um, yeah, it sounds like a very interesting application. It's probably something we could talk about offline as well. But that's the focus of Zach and my project that we're looking at right now. But for traditional insurance, I was trying to figure out how you could maybe fit that idea where the neural network would learn something that kind of falls between 0 and 1
Yeah.
in order to have it be an appropriate output. But I see what you're saying.
Yeah, happy to talk about this.
Thank you.
Yep. Anybody else? Okay, I'll leave it up to you, Rishaka, to see what you want to do now.
Yeah, we've got another question in the chat.
Okay.
It's a question about uncertainty. If more people sharing risk, will the randomness, like the catastrophic risk, vanish or reduce?
The risk itself doesn't change, doesn't vanish or reduce or anything. There's a risk that's given out there. And the question is how to optimally allocate the risk between individuals. We're not getting rid of the risk. The risk exists. We're just finding the optimal way to allocate it. If you want to get rid of the risks, you need to introduce an insurance company who will take care of that, not the individual. Okay. I hope this answered the questions. This answers the question.
Do we have any more questions? All right. If not, thank you so much, everyone, for joining today. And thank you as well, Professor, for an engaging and insightful session. I'm confident all of our participants took away a lot from your expertise. We appreciate you taking the time to be with us, and we're looking forward to welcome you back for future talks.
Thank you. Thanks for the invitation. And thanks, everybody, for coming.
Thank you, everyone. Have a great rest of your day.
Okay. Bye-bye.
You know.